Alright, this is example 2. I'm going to again assume that you've read this example, that you've tried to work this example on your own, and I'm going to get started with the solution. So, the problem describes an electron that is entering a uniform electric field that's created between two parallel plates. And based on the information that we're given, we could say that let's draw the parallel plates that the electron is going to travel through. So I'm going to call the plus x direction to the right and the plus y direction up. And so I've got a positive plate on top of a negative plate. And that means that I'm going to get an electric field created between those two plates that points from the positive side to the negative side. And I'm told to ignore the edge effects. So what does ignore the edge effects mean? Well, if we look at one of the slides that's included in the slide deck for this module, there's a picture of the exact scenario that we're talking about. A positive plate above a negative plate with a uniform field in between the two plates, except over here along the edges we have field lines that sort of curve around the edge. And so all I'm saying in this example problem is ignore this effect, just consider the uniform field. So let's say that outside the plates the field is 0, and inside or between the plates the field is non-zero and it's uniform. So that's what the edge effects statement is about. So we have an electron that's coming in with some initial speed, and that speed is just in the x direction. So the electron has a velocity vector that points just in the x direction. So the velocity of the electron is its x component times x hat, and we're told that this x component is 1,000 meters per second. A couple of other things that we know. We're told that the electric field strength inside the two plates is, let's see here, it's 100 newtons per coulomb. So let me just call the electric field strength just an E. That's the magnitude of the electric field between the plates, and that's going to be 100 newtons per coulomb. And then I also know that the plates are separated by some distance d, and that distance d is 1 centimeter. And then also note that the electron is going to enter the field at 1/2 of that. Right, so it enters the space between the two plates at a point that's halfway between those two plates. All right, so that's the setup of the problem that we have. Now, in order to find let's look at the two questions that were asked. The first question is, which plate will the electron collide with? So the electron is going to enter from the left here, and once it enters the electric field, it's going to have a force exerted on it, and it's going to collide with one of those plates. Now we know that the force that gets exerted on a charge is equal to Q times the electric field, and the charge Q can be positive or negative. If it's positive, we're going to have a force that gets exerted in the direction of the field lines. So if I've got field lines that point like this, I've got a positive charge here, then we're going to get a force that points in the direction of the field lines. If instead I have a negative charge, I'm going to get a force that is in the opposite direction of the field lines. And so we have an electron. We know that the electron is negatively charged, so it's going to have a force that is in the opposite direction of the field lines. That means that this electron is going to enter the field, and then it's going to be attracted to the positive plate, which of course we could also answer just by knowing that electrons are negative. They're going to be attracted to positive charges. They're going to be repelled from negative charges. So we expect this electron to be attracted to the positive plate. So the answer to the first question is it's going to collide with the top plate. Now the second question is, how long is it going to take for this to happen? So when we're dealing with a uniform electric field, we basically have a force that is constant. It does not depend on space. And that means that the acceleration of the charge in the uniform field is also going to be constant. So we can use the equations that we have for constant acceleration, so the kinematic equations that we used in the previous semester for constant acceleration, we can use those equations for these uniform field cases, because we know that the force that gets exerted on the charge is going to be the charge times the electric field strength. And that has to be equal to mass times acceleration. So that means that the acceleration is Q over M times E. And since the electric field is uniform, that means that it has the same value at all points in space. This is going to be constant. So this is a constant number. And that's all that we need to use the kinematic equations. We need constant acceleration. So recall that the kinematics equations, we have some equations that tell us what the position and the velocity as a function of time for a particle undergoing constant acceleration will be. And the way that they're written out in the the section of the book that discusses the kinematics in one dimension is that the position of a particle is going to be equal to its initial position plus its initial velocity multiplied by time plus 1/2 its acceleration times time squared. And then the velocity is going to be equal to its initial velocity plus its acceleration times time. So these are the kinematic equations. And when we have two-dimensional motion, meaning we have motion in the x and the y direction, then we basically just have a kinematic equation, or a set of kinematic equations for the x direction and a set for the y direction. So we can also write down a set of these for the y direction. So there are the kinematics equations that we can use to consider or to determine the velocity in the x and the y direction and the position in the x and the y direction as a function of time. So these are the equations that we'll use to figure out how long it takes that electron to actually collide with the top plate. So first, let's consider the acceleration. The acceleration of the electron, let me draw the electron here. So the electron has a negative elementary charge. The force is going to be in the plus y direction, so the acceleration is going to be in the plus y direction. So the acceleration vector is actually just going to be a y component, or it's just going to have a y component, right? So the acceleration in the x direction is actually 0. And the acceleration in the y direction we can find from the force of the electric field acting on that charge. So the acceleration in the y direction is going to be the charge of the electron, so I'm going to put negative E, divided by the mass of the electron. And then we have to multiply this by the y component of the electric field. But remember, the electric field is pointing down, so the y component of the electric field is actually negative. So this is going to be negative times the magnitude of the electric field, since it points just in the y direction, which means the acceleration is going to be the electron charge times the field strength divided by the electron mass. That's the acceleration in the y direction. So that means that the position in the y direction as a function of time can be written down in terms of this acceleration. So let me use the position equation for the kinematics, or the kinematics equation that describes position in the y direction. So the position in the y direction as a function of time is going to be its initial y position plus its initial y component of velocity multiplied by time, and then the acceleration term here. Now let me rearrange this. Let me put the y naught, or the y sub 0, over on the left side. And the reason that I'm going to do that is because we already know that y minus y naught is equal to the 1/2 centimeter, right? So the electron enters the field halfway between the positive and the negative plate. That distance is d over 2, and d over 2 is going to be equal to 1/2 centimeter. So I already know, this is a number that I have. This is d over 2, which means that this is d over 2. All right, let's look at the other terms in this equation. This is the velocity in the, hold on, I made a mistake here. Let me look at this. There shouldn't be an x subscript. This should be a 0 subscript. So this is the initial y component of the velocity of the electron. So as it enters the field, this is the y component of the velocity. And that velocity is 0 because we're told that the electron is traveling in just the plus x direction. So we know that this is going to be equal to 0. So really, we just have these two terms here. And we already know what this distance is, and we know what this acceleration is in terms of the field strength and the charge. So really, we can use this equation to determine what that time is. And so that's all we need to do. So let's use that equation to solve for time. So I'm going to write down, multiply both sides by 2, which means that time squared is going to be d divided by the acceleration. Take the square root of both sides to get time by itself, and then I'm just going to insert what I know for the acceleration, or what I calculated the acceleration to be in terms of the things that I know. And so that is right here. So I've got d m sub v over e square root of. And there we have it. That's going to be the time that it takes the electron to collide with the positive plate. So we've got positive plate on top, negative plate on bottom, uniform field in between. The uniform field must point from the positive side to the negative side. I have an electron which has a negative e charge coming in with some initial velocity that is just in the x direction. Once it enters the field, it's going to be accelerated towards the top. The x component of the velocity is not going to change, so the speed of the particle in the x direction is going to be constant this whole time. But it is going to be accelerated in the y direction, and so that velocity is going to increase. And then we just use the fact that because the field is uniform, the acceleration must be constant, and if we have constant acceleration, we can use the kinematics equations. And so we know that it's going to collide with the top plate, and we know that this is how long it's going to take it to collide with the top plate. We have numbers for all of these. The distance d is 1 centimeter. The mass of the electron is a number that can be looked up, right? It's in the book. The charge of the electron, or excuse me, this wouldn't be the charge of the electron. This is the elementary charge. The charge of the electron is negative of this. That is also a constant that can be looked up. And then the electric field strength is given to us. That's the 100 newtons per coulomb. So in this case, we're told that the initial speed of the electron is 1,000 meters per second, but that doesn't actually matter because the speed in the y direction, or the velocity in the y direction, is 0, and it's only the velocity in the y direction that is going to matter for this problem. And I tell you what, just so that we're all on the same page here, let me go ahead and write down what the mass of the electron is. So this would be the 9.1 times 10 to the negative 31 kilograms. And the elementary charge is 1.602 times 10 to the negative 19 coulombs. So when I calculate this time, I do have to be careful here because d I have in centimeters, but the other constants, or the other things that I have, like newtons, is going to have meters in it. So I need to unit convert to make sure that my centimeters will cancel with the meters that is actually in that newton. And in fact, I'll do that example in another video. So there's a follow-up video to this that will show how to make sure that we get the correct units to calculate this time correctly. But this is the answer. Now all we got to do is plug in the numbers that we have.